Many quantities that we work with in mathematics and related fields can be described using a single real number. Things like area, temperature, bank account balance can all be represented by just a single number. However, some quantities need to carry both the information of a magnitude and a direction with it. Things like this would include the velocity of something, where you want to know whether something is moving north, south, east, or west in addition to how fast it's moving. Or when you want to know the forces that are acting on a given object. You want to know both how strong those forces are and in what direction they are pushing. These are two different types of quantities we look at, and we call them scalars and vectors. So a scalar is a quantity that can be described using a single number. Whereas a vector is a quantity with both a magnitude, which describes how big the quantity is, and a direction, which tells you in which direction the quantity is moving. Now, of course, whether or not that makes sense depends on what kind of quantity you're describing. We have various ways of talking about vectors and thinking about them. One of the most basic and intuitive is to use arrows, which have both a magnitude, which can be associated to their length, and a direction, which is the direction that the arrows go. So, given points P and Q, we can talk about the vector, which we denote this way. PQ with an arrow over it going from P to Q. From P to Q like this, and then we have something like that. So you'll notice that this quantity, this vector here, has two components to it. It has a magnitude, which is measured by the length of the arrow, and it has a direction, which is indicated by which direction the arrow is pointing. We can think of vectors as being directed line segments. So this is the segment from P to Q with a direction chosen here. Now, you may notice that we're using the same notation for this as we use for rays in geometry. So we would use this notation for the ray that starts at P and passes through Q. It is the same notation. We're talking about different things. In practice, it rarely causes an issue, but if there's ever any confusion, we will be precise about what we mean. So this is one way that we can describe vectors, is by describing a starting and ending point for a line segment here. Often we want to talk about vectors without describing specific points. And so we might look at this vector here, and I'm going to choose a vector which is in the same direction and with the same magnitude, and I'm going to call that vector U. And in print, these vectors are usually indicated by using boldface type. When working by hand, we usually indicate it with a little arrow underneath. Now, an important point to remember about vectors is that vectors don't care about where they're located. That is where they start, where they end. They only care about their length, that is magnitude, and their direction. So for instance, we've got these two vectors here that I've written out. We've got the vector PQ and the vector U. Now, they are sitting on different spots on the page, but they are going in the same direction and they have the same length. And because of that, we say that these two vectors are actually the same. The starting point of a vector does not affect it, and a vector is the same no matter where on the page you put it, as long as it's still going in the same direction and with the same length. Now, vectors are very, very useful for all sorts of situations that we want to describe. One of the places where we use vectors the most is when working in physics. So, an example of how we might use physics is, let's say there's an object here that's being suspended from the ceiling. And it's being suspended from the ceiling using two chains, which are forming certain angles with the ground. Let's say this one is forming an angle of 45 degrees with the ground. This chain is forming an angle of 30 degrees with the ground. And there are certain forces acting on this object. We have the force due to gravity, which is pulling straight down. Then we have the force of each chain, which is pulling on the box in different directions. And if the whole system is not moving, if the box is actually suspended there and it's just staying there, then in fact all of these forces will be canceling each other out. And using some of the techniques that we're going to do today to figure out how to turn these angles into vector notation, ways that we can measure vectors, we can do some algebra to figure out, okay, well, how much force is being exerted by, say, each of the two chains in the problem. So that's just an example of how we might use vectors here. Now, as I said, in a situation like this, we are interested in knowing the combined effect of all of the forces together on the box. The way that we interpret that in the problem is, mathematically, is by adding the vectors together. We want to have some notion of how to add vectors together. So, addition of vectors. So given given vectors u and v, the vector u plus v is obtained by moving the initial point of v to the end of u, then forming the vector from the start of u to the end of v. So what I mean by that is, if we want to add together the two vectors, we'll say the vector u and then the vector v. The way that we do that is we actually take the vector v. Now remember, we can move it around without changing it. These are all the same vectors no matter where where I choose to put it. And so in particular, I can choose to put it here so that the base of v is at the end of u. Then I can connect up the beginning of u with the end of v to get a new vector here. And this vector is the vector u plus v. Now, one way of thinking about this that helps with this way of describing what's going on, or thinking about what's going on, is that u and v can describe displacements, that is motion that's actually being taken by an object. So the vector u could describe taking an object and moving it a certain distance in a certain direction, and the vector v can represent taking an object and moving it a distance in a particular direction. And so the vector u plus v describes the displacement, that is the net motion that's obtained by first moving an object along u, in the direction of u and the distance of u, and then in the distance and direction of v, that is along the vector v. And so this is one way of thinking about the addition of vectors. Another way that's useful for problems like the one that we had above, where we've got a whole bunch of forces acting on a single object, and it's useful to think of all of our vectors starting in the same place, is the following. Alternatively, we could do this. If we have the vector u and the vector v, I'll give them labels here. What we can do is we can form the parallelogram that we get by basically copying, or rather finding the parallelogram that these two vectors form the sides of, which looks about like that. And if we do that, then the vector from one corner to the other, the corner that u and v start at, to the opposite corner, is also u plus v. That's another way of thinking about it that makes a little bit more intuitive sense when you think about u and v as two different vectors operating on the same object at the same time. So this is how we can add vectors together, again, intuitively. We'll get into the algebra of how all this works in a moment. There's another operation that we can do with, or there are a few more operations rather that we can do with vectors. So let's talk about vector subtraction. Let's say we've got vectors u and v, and I want to know what is u minus v. Well, if the algebra of vectors works in the way that we expect it to, we should have that the vector v plus the vector u minus v equals the vector u. As I said, if vector subtraction works at all logically and consistently with other algebraic operations that we have. So the way that we see how that works here is the following. Let's go ahead and consider a couple of vectors u and v. And see what we need here. The vector u minus v should have this property right here, that if we take the vector v and we add the vector u minus v, whatever that is, then we should get u. Well, consider this green vector right here. Whatever this green vector is, let me call it w for the moment, we definitely have that u is equal to v plus w. But that means that this w here is playing exactly the role that we want u minus v to solve. So that means that w should equal u minus v. Or in other words, if you want to think about it this way, which works, we can take this this equation, u equals v plus w, subtract v from both sides to get that this w here is actually the same thing as u minus v. So this tells us that the vector u minus v goes from the end of v to the end of u when u and v have the same start point. So that's how we can subtract a couple of vectors. The third operation that we've got is a form of multiplication. However, it turns out that multiplying vectors together is more complicated than just multiplying numbers together. We're going to have some different ways of understanding what it means to multiply things involving vectors. The most basic one is what we're going to call scalar multiplication. So scalar multiplication. Given a vector u, the vector a times u, where a is a real number, is one of two things. If a is greater than 0, then a times u is in the direction of u, but its length has been multiplied by a. So for instance, if a is 2, then 2 times the vector u will be a vector that goes in the same direction as u, but is 2 times as long. If a is 1/3, it'll be a vector that goes in the same direction as u, but is 1/3 as long. And then if a is less than 0, if a is negative, then a times u is in the opposite direction of u, and its length has been multiplied by the absolute value of a. So let's see some examples. Let's say we're starting off with the vector u, and let's say we want the vector 2u. Well, that's going to be a vector that goes in the same direction as u, but is twice as long. Let's say we want the vector negative 1/2 u. That's going to be a vector which goes in the opposite direction of u and is half the length. We can do this with any real number a here. This is called scalar multiplication because the number a is a scalar. It's a single real number. And so with scalar multiplication, we're taking a scalar and a vector, multiplying them together and getting a new vector out of it. And that's what gives us scalar multiplication. This is very useful in situations where you're told that, for instance, this object is moving twice as fast as this other object, but in the same direction. Or if one force is, only 1/3 as strong as some other force, but going in the same or the exact opposite direction. Notice that scalar multiplication always gives you a vector, but it always gives you a vector that is pointing either in the same direction as the original vector or in the opposite direction as the original vector. It will never give you a vector that points in any other direction than those two. All right, so now we want to see how we can start using algebra to do things a little bit more precisely with these vectors. Working with the pictures and the arrows is very, very good for our intuition, and we're going to keep coming back to this often. However, we often need to be more precise about it. So for this, we're going to now make sure that we're on a Cartesian plane, that is a grid with x coordinates and y coordinates and so forth. So let's go ahead and do that. So let's suppose that we are on a Euclidean or Cartesian plane rather, with standard coordinates here. And let's suppose we just have some random vector sitting out here in the plane. Some random vector v. Well, as we said, we can take this vector v and we can move it anywhere in the plane, and it's still, they're all still equal. The vector doesn't care about where it starts, only its direction and magnitude. But that means that we can choose, if we like, to look at a version of the vector that sits in a particular place. And the one that we want to look at is the one where the base of the vector, the starting point of the vector, is at the origin. So, for a given vector v, the position vector for v is the equivalent vector with its start at the origin. Now, when this is the case, the position vector for the vector v has a particular endpoint. It's got a particular endpoint over here. And that point has coordinates. In this case, the coordinates of this point are 3, 4. And we're going to use this 3, 4 to to describe the vector v. So the coordinates of the endpoint of the position vector of v are called the components of v. And if these coordinates are a1, a2, if that's the coordinates of the endpoint of this vector, then we write that V is equal to the vector with components a1, a2. So notice that in this notation we're using angle brackets on either side of the coordinates a1, a2. So in our example up here, we would write that this vector v is the vector 3, 4. Now, it's important to note that the points that we use here don't depend on where the actual vector we're looking at is located. If we've got some vector here, say, we've got the vector u, the components of u are determined not just by the endpoint of this vector, but by the difference between the starting and endpoints of the vector. So another way of looking at this is to say that if a vector, I'll say u now, goes from the point, I don't want to use a1 and a2 again. If it goes from the point b1, b2 to the point c1, c2, then the vector b has coordinates of c1 minus b1, comma, c2 minus b2. So if we've got the vector u and we know its starting and ending points, we can determine its components by simply subtracting the coordinates of the starting point from the coordinates of the ending point. So for instance, this point u, or this vector u, goes from the point -5, 5 to the point -2, 4. And so that tells us that the vector u increases the first coordinate by 3. It goes from -5 to -2, and therefore the first component of this vector u is 3. And then in the second component, we see that we've gone from 5 to 4, which means that the vector has decreased the y value of the points by 1 from its beginning to its end, and therefore this vector u has coordinates, or it has components 3 and -1. Most of the time when we do algebra with vectors, we're going to be doing it using the component form of the vector. It is by far the most easy way of doing arithmetic with these vectors. So there are a few things that we want to talk about when working with vectors like this, in this form. So let's first talk about the magnitude. The magnitude of the vector v with components a1 and a2 is, actually, sorry, let me be more consistent. Most of the time, or much of the time I should say, we use notation for the components that are related to the notation that we're using for the vector. So we'll talk about the vector A with components A1 and A2. So to find the magnitude of a vector with components A1 and A2, we can look at the position vector. We know that the position vector here goes from the point 0, 0 to the point A1, A2. That's the definition of the position vector. And this vector now lies on the hypotenuse of a right triangle. Now the lengths of the sides of this right triangle are a1 and a2, which means that the hypotenuse has length a1 squared plus a2 squared. And it turns out it doesn't matter if a1 or a2 are negative because we wind up squaring them, which brings everything back to positives anyway. So the magnitude of a is, well, it's given by this formula, the square root of a1 squared plus a2 squared, but it also has the notation, the magnitude of a. Now, this, you'll notice, has a notation that looks like absolute value, but it's got double bars on either side. That's the notation that we use for the magnitude of a vector, which behaves in some ways like an absolute value, but not exactly the same. So let's see a couple of examples of how we use this. Let's find the magnitude of the vector 2, 3. Well, the magnitude of the vector 2, 3 always follows the same formula. And you can remember it because it's the same as the formula for the hypotenuse of a right triangle. So the magnitude of the vector 2, 3 is equal to the square root of 2 squared plus 3 squared, which is the square root of 4 plus 9, which is the square root of 13. And that's pretty much all there is to it. I can't really do a whole lot more examples. So if I ask you to find the magnitude of -6, 5, we're going to get something very similar. The magnitude of -6, 5 is equal to the square root of -6 squared plus 5 squared, which is going to give us the square root of 36 plus 25, which is the square root of 61. So the magnitude of a vector is given just by this formula right here. Now, actually knowing the magnitude is very, very important in many cases. But before we can start seeing those applications, we need to look at some of the other things that we can do with vectors. So the next thing that we want to do is talk about how we add and subtract and scalar multiply vectors when they're in their component form. And the good news is that this works in the simplest way that we could want. So let's look at addition of vectors using their components. So let's just give a quick example here. Let's say I've got the vector A, which is 3, 2, the way I've graphed it here. And let's say I've got the vector B, which is the way I've drawn it here, -1, 4. Now, you'll remember that the way that we actually find the sum of a couple of vectors is to move one of the vectors to the end of the other one. Oops, sorry about that. And look at what's happening from the beginning of the first one to the end of the second. Well, remember that a vector is basically just telling you what the difference is between the starting and end points of that vector. So for instance, this point, the actual point on the graph right here, is 3, 2, which means that if we start at 3, 2, and then we travel by the vector b. The vector b says we're going to decrease the x-coordinate by 1 to get to 2, and increase the y-coordinate by 4 to get to 6. So that means that the vector a plus b, in this case, is equal to the vector 2, 6. But you'll notice that's also what you get if you just add corresponding coordinates of the two vectors that we started with. So the vector 2, 6, by our analysis here, is the sum of the vectors 3, 2 and -1, 4, but that's also what you get if you just add the first components together, 3 plus -1, and add the second components together to get 2 plus 4. And in fact, this always works. So the fact that we will use very often is that the sum of two vectors, a1, a2, and b1, b2, is simply what you get by adding component-wise. a1 plus b1, comma, a2 plus b2. And this shows one of the ways in which using components for vectors is very easy. Adding vectors is very, very easy when you have their components. Similarly, if we want to subtract two vectors in their component forms, we simply subtract them component-wise. So the vector a1, a2 minus b1, b2 is the vector a1 minus b1 and a2 minus b2. And then similarly, if we have a scalar multiple, let's say we've got a number c here, and we want to multiply it by the vector a, so that's c times the vector a1, a2, we get that by taking the scalar multiple c and multiplying it by each of the components inside. So when doing arithmetic with vectors, addition, subtraction, and scalar multiplication, the way to remember what to do is that you just do whatever the expression says on each component of the vectors that you're working with. So let's see some examples of how this works. So let's simplify 2 times the vector 1, -1, plus 3 times the vector 2, 6. So if we have 2 times the vector 1, -1, plus 3 times the vector 2, 6, well, we start with the scalar multiplication because order of operations still applies here and multiplication still comes before addition. So if I have the scalar 2 times the vector 1, -1, I'm going to take that 2 and multiply it by each of the components inside. So 2 times 1 is 2, 2 times -1 is -2. Next, I'm going to take the 3 that's in the second term and multiply it by each of the components inside the vector there. Now, to add together the vectors that I've got after doing the scalar multiplication, I simply add first terms together. So 2 and 6 add together to give 8, and then -2 and 18 add together to give 16. So the simplification of the expression 2 times the vector 1, -1, plus 3 times the vector 2, 6 is the vector 8, 16. There is one very special vector that we see. It's called the 0 vector, and we often denote it with this notation, 0 with an arrow above it. meaning the 0 vector, and it's the vector with zeros in each of its components. Now, this is the only vector that doesn't have a well-defined direction to it, and it's also the only vector that has a magnitude of 0. If our vectors are representing velocities, for instance, the 0 vector represents an object that's at rest, that is not moving at all. And if I've got an object that's not moving at all, then it doesn't make sense to say that it's moving in any particular direction. But we can say that the magnitude of its velocity is 0. So we do have the 0 vector, and it behaves in a lot of ways like the number 0. So for instance, if I have a vector v and I add the vector 0 to it, I'm just going to get the vector v back because the vector 0 doesn't actually move anything anywhere. All right, so we've got these rules for arithmetic on vectors, and there are lots of properties of this arithmetic that are very familiar to us because they're the same as the properties for real numbers. I'm just going to quickly run through a few of the most important properties here. None of them are surprising, and all of them can easily be seen just by breaking down the vectors into their component pieces and doing the operations we're about to see. So we have the following facts. If I have two vectors a and b, then a plus b is the same as b plus a. Scalar addition is commutative. If I have three vectors a, b, and c, and I group them up one way, that's the same. I get the same result as if I group it up the other way. So this is the same as saying that vector addition is associative. If I take a plus the 0 vector, I just get a back. Mentioned that just now. If I take a plus negative a, I get the 0 vector. Now here I should mention that when we write negative a, this is just a shorthand for negative 1 times a. So it's what you get when you turn every component of the vector a or you change the sign of every component of the vector a. Multiply each component by negative 1. If I have some constant, some scalar, and I multiply it by a sum of vectors, that's the same as what I get if I do the scalar multiplication first on each of the vectors and add them. So this is saying that scalar multiplication distributes across vector addition. And then similarly, if I have two scalars and I add them together, multiply by a, that's the same as if I take the two scalars, multiply by a separately and add them. So this tells us that scalar multiplication distributes across addition of scalars as well. If I have a product of scalars, then and I'm doing that scalar multiplication with a, that's the same as taking, as grouping things up this way, doing the scalar multiplication of n first and then the scalar multiplication of m, but it's also the same as if I take the scalar multiplication in the other direction. So this is sort of an associativity of scalar multiplication. If I take the scalar multiplication 1 times a, then that just gives me 1, or gives me a back. And if I take the scalar multiple of a vector with the number 0, I get the 0 vector back. So all of these facts should hopefully be fairly intuitive. They're really just duplicating the facts that we know about the real numbers. Now, certain vectors are special and useful to us, and they're called unit vectors. A vector is called a unit vector if its magnitude is 1. Unit is a word that doesn't exactly mean 1, but is often used analogously. So a vector is called a unit vector if its magnitude is 1. Now, often we want to find the unit vector in the direction of a given vector. The unit vector in the direction of u, of the vector u, is given by, well, we know that we find a vector in the direction of another one by taking a scalar multiple of it. That's what scalar multiples do. Now, whatever the magnitude of u is, if we want a vector that has a magnitude of 1, we need to reduce the magnitude of u to 1, or possibly increase it if it's smaller. Turns out what we want to do is we want to take a scalar multiple of u where the multiple is the reciprocal of the magnitude of u. Because this vector 1 over the magnitude of u times u will be a vector in the direction of u, but its magnitude will be 1, because we're just dividing by what the length of u was to begin with. So, for example, we might be asked to find the unit vector in the direction of, let's say, A, which is the vector 3, 4. So the solution is, first, we want to find the magnitude of A. So finding the unit vector always takes 2 steps. The first is finding the magnitude of the original one. You need to figure out basically what you need to change it by. So the magnitude of A is equal to the square root of 3 squared plus 4 squared. Now 3 squared is 9 and 4 squared is 16. And so that tells us that the magnitude of A is the square root of 25, which is 5. So currently the vector A has a magnitude of 5. Therefore, if we want a vector in the same direction as A, but with a magnitude of 1, we need to take A and divide it by 5. So that means that the unit vector in the direction of A is 1 over 5 times A, which is 1 over 5 times the vector 3, 4, which we can get by multiplying 1/5 by each of the numbers inside. So that's 3 over 5, comma, 4 over 5. Now, in terms of the graph, what we're doing here is we're taking a vector, A, with coordinates, or with components rather, 3/4, 3, comma 4. And then we're basically shrinking down this this vector until it has length 1. So here we have the vector, we have the vector 3/4, 3/5 rather, 4/5. So it's in the same direction as A, but it has length 1. Now, we can continue this process to get vectors with any length at all, either in the same direction as A or in the opposite direction as A. Let's find a vector with length or magnitude 7 in the opposite direction to the vector b, which is 3, -2. Now, there are two steps that you will typically want to take with a problem like this. Step 1 will be finding a unit vector in the direction of b, and then step 2 will be finding the vector with the length that you want in either that or the opposite direction. So step 1, find the unit vector in the direction of b. So let's do that. So for this, we need the magnitude of b, and the magnitude of b is going to be the square root of 3 squared plus -2 squared, which will be the square root of 9 plus 4, which is the square root of 13. So that means that the unit vector, which I'll go ahead and denote by u for unit, is 1 over the square root of 13 times b, which gives us 3 over the square root of 13, comma, -2 over the square root of 13. So there's our unit vector that's in the direction of b. So now, for step 2, let's get the magnitude and direction we want. Well, so we know that we're going to get this by multiplying by a scalar. Now, the unit vector u has magnitude 1, so if we want a vector with length 7, with magnitude 7, we're going to multiply by 7, but because we want it in the opposite direction, we're going to multiply by -7. So we get -7 times u is equal to -7 times the vector 3 over the square root of 13, comma, -2 over the square root of 13, which gives us, let's see, -7 times 3 over square root of 13 will be -21 over the square root of 13. Then -7 times -2 will give us positive 14 over the square root of 13. And there is our vector with length 7 and in the opposite direction to the vector b. There is an alternative way of describing vectors which is equivalent to the component form that we've seen so far, but is more commonly used in certain industries or disciplines. To see how this works, note that there are a couple of special unit vectors that we can look at. And they are the vectors 1, 0 and 0, 1. So we can look at these vectors here. And they have special names associated to them. The vector 1, 0 has the name I, and the vector 0, 1 has the name J. So this is just a definition, or really a notation. The vector I is simply the vector 1, 0, and the vector J is the vector 0, 1. Now, the reason why we might care about these is that every vector can be expressed as a combination of these two vectors. Now, this isn't the only pair of vectors that statement is true for, but they are sort of the easiest to work with. And we say that these two vectors form a basis for all of our vectors. So any vector can be described in terms of I and j. And we can see that in the following way. Let's take as an example, if we want to look at the vector 3, 4, we can use vector addition in the backwards way from the way that we normally do, to write 3, 4 as the vector 3, 0 plus the vector 0, 4. Then in each of these cases, we can basically factor out a number by scalar multiplication, and we could write this as 3 times the vector 1, 0 plus 4 times the vector 0, 1. But that's exactly the vectors I and j. So instead of writing the vector 3, 4, we could write the vector 3i plus 4j. Now, there's nothing special about 3 and 4 here, and indeed, if we take any vector a1, a2, this can be written as a1i plus a2j. Now, one advantage that writing things down this way does do for us is it allows us to treat I and j, the vectors I and j, as variables when doing arithmetic. So let's see how that goes. So let's find 3i plus 4j plus 6i minus 7j. Well, if we do that, then first of all, let's do this problem in the way that we're already familiar with. We know that 3i plus 4j is another way of writing the vector 3, 4. And the vector 6i minus 7j is another way of writing the vector 6, negative 7. And we know that to add these two together, we just add the corresponding components together. 3 plus 6 is 9, 4 plus negative 7 is negative 3. Well, let's see how this works when we continue using the i's and j's here and treat them like variables. If we have 3i plus 4j and 6i minus 7j, we can rearrange this to gather sort of all the i's together. So this is 3i plus 6i plus 4j minus 7j. And now, if we treat, again, these i's like variables, then 3i plus 6i is just 9i. We know that we add expressions by adding the coefficients. And then 4j minus 7j is negative 3j, which you'll notice is in fact the same as the answer that we got before. However, working with the i's and j's just gave us another way of doing it. Let's look at another example. Let's find 3a plus 5b if a is equal to 5i plus 6j and b is equal to negative 3i plus 4j. So here, again, we can treat the i's and j's like variables and simplify the expression 3a plus 5b, see what we get at the end, and that'll be our vector. So we'll take 3 times a plus 5 times b, and that's 3 times the vector 5i plus 6j plus 5 times negative 3i plus 4j, which gives us 15I plus 18j plus negative 15I plus 20j after distributing the constants on the outside through. Again, this is just scalar multiplication when writing things down using the vectors I and j. Now combining these, you'll see we've got a 15I and a negative 15I. Normally we would just not write that when one of our terms cancels out, and so that's what we're going to do here. So we get a 0I plus 38j, and then we'll just write it as 38j. This is something that you will occasionally run into when expressing your vectors using the basis vectors I and j. Sometimes you'll get expressions that don't include an I or don't include a j. In that case, to translate it into component form, then any either of these that don't appear has a corresponding component in the vector of 0. So the vector 38j is in fact just the vector with components 0, 38. And so that's how we can use I and j. Now let's see how we can use some of our trigonometry in order to convert certain vectors that are expressed using angles into their component form. So let's say that we had a vector that is given to us with its magnitude and its direction, but let's suppose that its direction is given to us in terms of an angle, like theta here. And let's say we're given that the magnitude is A. So our problem here is to find the components of the position vector with length A and in the direction given by theta in standard position. That is starting at the positive x-axis and moving counterclockwise. Well, we can use what we know about trigonometry here. We know that the point on this vector that is a distance of exactly 1 away from the origin lies on the unit circle. And therefore, we know that this vector has coordinates, or rather, sorry, this point here has coordinates cosine theta, sine theta. That's how we defined sine and cosine way back at the beginning. So let's see, what do we know? We know that the unit vector in the direction of our vector, oh, I haven't given the vector a name. Let's call this vector v, this whole thing v. So we know that the unit vector in the direction of v is the vector with components cosine theta and sine theta. Any vector, by the way, with components of cosine theta and sine theta is always a unit vector. So, since the magnitude of v equals a, that means that we have that v is a times the unit vector in the direction of v, because this will be a vector in the same direction as v, but with length a. Therefore, it will be v. So it will be a cosine theta, a sine theta. So this turns out to be quite useful to us. So the answer to the question of what the vector is with a length of a in the direction of theta in standard position is a cosine theta, a sine theta. This winds up being quite useful to us. Let's see how we can use this in an application type problem. Let's say that an airplane is traveling due east at 500 miles per hour relative to the air. However, the wind is blowing at 120 miles per hour due northwest. What is the what is the velocity of the plane relative to the ground? All right, so for this, let's set up our situation and sketch out what's going on. Let's go ahead and set up a coordinate system for ourselves, and let's go ahead and set it up in the normal way, north, south, east, and west. So we've got two vectors being described here, two velocities. One of them is the velocity of the plane. We're told that the plane is traveling east at 500 miles per hour. We're told that the wind is blowing directly northwest at 120 miles per hour. We want to know what the velocity is of this plane relative to the ground. Now that's going to be given by the sum of the two vectors involved, because the plane is traveling at 500 miles per hour east relative to the air, but the air itself is blowing north and west. So we can see that our final speed is in fact going to be given by the sum of those two vectors. So that green vector there is what we're looking for. So if we, if we let A be the velocity of the plane, the air velocity of the plane, and W the velocity of the wind, then we want A plus W. And that's what this is right here. Now, in order to actually figure out what this vector is, typically we're going to want components to it. Now, the A component is not too difficult because we can see that we've got a vector with length 500 that's going straight to the right on our set of axes, and so the vector A is simply the vector 500, 0. On the other hand, the vector W we're going to have to compute using the stuff from last time, or from the last slide. So we can see that the wind vector here is going in a direction of 135 degrees. It's blowing straight northwest, which means that it's blowing exactly halfway in between straight up and straight left. That forms an angle of 135 degrees. We also see that it has a magnitude of 120, which means that the components of the vector W are 120 times cosine 135 degrees, comma 120 sine of 135 degrees. Now, cosine of 135 degrees is negative 1 over the square root of 2. So we actually get negative 120 over the square root of 2, comma, 120 over the square root of 2, because sine of 135 degrees is 1 over the square root of 2. So, given these two things, we can figure out a plus w. So a plus w, the vector a plus the vector w will be 500 minus 120 over the square root of 2, comma, 120 over the square root of 2. And we can approximate this using a calculator, which equals approximately 415, 85 in a calculator. So this tells us that the vector, which corresponds to the velocity of the plane, has components 415, 85. From this, we can tell a couple of things. For instance, we could find the speed of the plane. The speed of the plane is just the magnitude of the velocity, which we get using our standard magnitude formula. So that'll be the square root of 415 squared plus 85 squared, which is approximately, again in a calculator, 406. So the plane is traveling at approximately 406 miles per hour. We can also use this information that we have, that this point here is at approximately 415, 85, in order to figure out this angle theta, in order to figure out the direction that the plane is traveling. So this is a triangle with side lengths of 415 and 85, and therefore if we want to find the angle theta that the new direction of travel of the plane is making with the eastward direction, this is going to be the inverse tangent of 85 over 415. Because we know that tangent of theta is 85 over 415, so theta is inverse tangent of 85 over 415, which is approximately 11 degrees. So, taking the wind into account, the plane is traveling at a direction that's mostly east, but 11 degrees towards the north, and is traveling relative to the ground at a speed of 406 miles per hour. And this is one of the simplest ways in which we can use vectors to really understand what's going on in a physical type problem.